In this video, we'll talk about computing trigonometric limits. Limits that involve trigonometric functions and have indeterminate forms, like 0 over 0, are sometimes called trigonometric limits. The most important example is the limit as theta goes to 0 of sine of theta over theta. This limit equals 1, which we proved in an earlier video using the squeeze theorem. It is usually possible to compute other trigonometric limits by making use of this one, which we'll see in our first example. Our first example is the limit as theta goes to 0 of cosine of theta minus 1 divided by theta. The first thing to notice is that this is an indeterminate form of the type 0 over 0. As theta goes to 0, the numerator goes to cosine of 0 minus 1, which is 1 minus 1, which is 0. The denominator is just theta, so as theta goes to 0, the denominator goes to 0. So this is an indeterminate form of the type of 0 over 0. It turns out that this limit does exist, and we can show that by manipulating the expression and working in the limit from the previous slide, namely the one involving sine of theta over theta. So how is this going to work? Well, we start with the limit as theta goes to 0 of cosine of theta minus 1 divided by theta. We're going to multiply this by some fraction. And it's going to be the same thing in the numerator as the denominator, so we're really multiplying by 1. And the thing we're going to multiply by is cosine of theta plus 1. If we put it in the numerator, we have to put it in the denominator as well, cosine of theta plus 1. Now the reason we're interested in multiplying by cosine of theta plus 1 is we're setting up the difference of squares in the numerator. So notice we have a cosine of theta minus 1 and a cosine of theta plus 1. So the basic idea here is we're treating cosine of theta minus 1 as a minus b and cosine of theta plus 1 as a plus b. A times, or rather a minus b times a plus b is the difference of squares, a squared minus b squared. And that's what we're hoping to achieve in our numerator. So we'll end up with the limit as theta goes to 0 of a squared, well that's cosine of theta quantity squared, minus b squared, which is 1 squared. Now of course 1 squared is just 1. And in the denominator we're not doing anything, we're just going to leave it as theta times cosine of theta plus 1. This numerator we're going to rewrite using the Pythagorean theorem. If we start with the Pythagorean theorem, we have cosine of theta squared plus sine of theta squared equals 1. If we subtract 1 from both sides, and then subtract sine of theta squared from both sides, we see that we have cosine squared minus 1 is the opposite of sine theta squared. Here we have in the numerator cosine theta squared minus 1. So we're just going to take this cosine theta squared minus 1 and replace it with sine of theta squared, or rather minus sine of theta squared. So that means we have the limit as theta goes to 0 of the opposite of sine of theta quantity squared, and then divided by, again, we haven't done anything to the denominator. It's just theta times cosine of theta plus 1. Now we're going to just rewrite this slightly. So it's the limit as theta goes to 0, and we're going to write this as minus, and then we'll write sine of theta squared as sine of theta times sine of theta. Now below the first sine of theta, we're just going to write theta. And then below the second sine of theta, we're going to write the rest of the denominator, cosine of theta plus 1. So now we have two fractions. And of course we have the minus sign in front. This minus sign is just that minus sign. So if we just mark that, this minus sign is that minus sign. Notice that we have a sine of theta over theta. This term is going to 1. So let's just write that down. This term is going to 1 as theta goes to 0. What about this other term here? Well, this term is not indeterminate. This is not an indeterminate form. We're not dividing by 0. The numerator is going to 0, but the denominator is not. The denominator is going to 1 plus 1 is 2. So this expression is continuous at theta equals 0. So this is just going to go to sine of 0, that's supposed to be a 0, sine of 0 divided by cosine of 0 plus 1. But that's just 0 over 1 plus 1, which is 2. Of course that's 0. So we end up with the opposite of 1 times 0, which of course is 0. So this 1 belongs to this sine of theta over theta, and this minus sign here belongs to this minus sign, and then we just have this remaining term right here, and that goes to 0, so that's this one. So what we have is that the limit, therefore, the limit as theta goes to 0 of cosine of theta minus 1 divided by theta is equal to 0. For our next example, let's look at this one. The limit as x approaches 0 of tangent of 2x divided by x. So in this case, what we're going to do is we're just going to rewrite tangent. So this is the limit as x goes to 0. Tangent is sine over cosine. So this is sine of 2x divided by cosine of 2x. And all of that is divided by x. Well, we can just rewrite this as the limit as x approaches 0 of sine of 2x divided by x times cosine of 2x, because dividing by x is the same as multiplying by the reciprocal. Okay, so I'm just going to rewrite this as the limit as x goes to 0 of sine of 2x over x times 1 over cosine of 2x. Now what you'll notice is that this still has that indeterminate form. It's still 0 over 0, but we've isolated it into this term. As x goes to 0, this term right here is fine. That just goes to 1. This term right here, this term, this goes to 1 over cosine of 0, so that just goes to 1. But what about this term? What does that go to? Well, it looks an awful lot like something that we've already seen. It looks like sine of theta over theta, except it's not quite because there's a 2x here and just an x here. What we want to do is we want to use sine of theta over theta. We want to use the limit as theta goes to 0 of sine of theta over theta equals 1. And we want to do that with theta equals 2x, because then we'd have a little theta right here. The problem is we don't have theta in the denominator, but we almost do. We have a 2x, and we only have an x, but you just put a 2 there. Of course, if you put a 2 in the denominator, you have to put a 2 in the numerator as well. So what do you have now? Just putting all this together, you're going to have the limit as x goes to 0 of 2 times sine of 2x over 2x times 1 over cosine of 2x. Now, if a limit exists, you can write a product as the product of the limits. So this is going to be 2 times the limit as x approaches 0 of sine of 2x over 2x times the limit as x goes to 0 of 1 over cosine of 2x. So you can take a limit of a product and write it as a product of limits provided all of those limits exist. which they do here. So this limit right here, that's the limit as x goes to 0 of 1 over cosine of 2x. So this is just 1 over cosine of 0, which is just 1. And this limit right here, this is actually the same as the limit as theta goes to 0 of sine of theta over theta, which we know is 1. And what do we have in front? We have a 2. So this is 2 times 1 times 1 is 2. And that's our answer. So the limit as x goes to 0 of tangent of 2x over x is 2. And we were able to compute that by making use of this sine limit, sine of theta over theta. Because we just rewrote this, we wrote this term right here, sine of 2x over x. We put a 2 in the denominator, and we had to put a 2 in the numerator, and then we had sine of theta over theta. And as x is going to 0, 2x is certainly going to 0. So as x goes to 0, theta goes to 0 because theta is 2x. Let's do another example. Here we have the limit as x goes to 0 of sine of 3x over sine of 4x. So how are we going to do this? Well, this doesn't look like a sine x over x kind of situation, but actually it is. This is the limit as x goes to 0 of sine of 3x over, and I'm not going to put sine of 4x under there. Instead, I'm going to do times, and then I'm going to put sine of 4x over here. What I'm going to do is in the denominator, I'm going to put an x, but if I put an x in the denominator, I have to put one in the numerator as well. So notice I can get away with this because there's an x here and an x here. X is going to 0, but it's not actually 0. When you compute a limit as x approaches 0, that means x actually isn't 0 itself. So that means I can divide by it. But of course, if I divide by it, I have to multiply it by it as well. But that's actually what we want, because notice we have a sine of 3x over x, and we can make that look like sine of theta over theta if we just put a 3 right there in the denominator. Of course, if you put a 3 in the denominator, you have to put one in the numerator as well. So we just put a 3 there. And what about this term? This isn't sine of theta over theta, but it's theta over sine of theta. It's the reciprocal. I just need to put a 4 here. But of course, if you put a 4 in the numerator, you have to put it in the denominator. Well, let's not put it there. Let's put it over here. So then, what do we have? We have 3 over 4 times the limit as x goes to 0 of sine of 3x over 3x times the limit as x goes to 0 of 4x over sine of 4x. Well, in this first limit, this is the sine of theta over theta. So this is the limit as theta goes to 0 of sine of theta over theta. Where in this case, we have that theta is equal to 3x. What about the other one? The other one here, this is the limit as theta goes to 0 of theta over sine of theta. Where in this case, theta is equal to 4x. Well, we know that this first limit here, the limit as theta goes to 0 of sine of theta over theta, we know that that's equal to 1. So we know that this one is equal to 1. But what about this limit? Well, this is not sine of theta over theta, but it's the reciprocal. This is just 1 over. Well, if sine of theta over theta goes to 1, then its reciprocal goes to 1 over 1, but that's also 1. Let me just move this just a little bit to the right, like so. So that means that this limit, that means that this limit goes to 1, and also this limit goes to 1. Both of these limits go to 1. So what do we end up with? We end up with 3/4 times 1 times 1, which of course is 3/4. So the limit as x goes to 0 of sine of 3x over sine of 4x is 3/4. You might notice that there's a 3 here and a 4 here, and we end up with 3/4. That's not a coincidence, but also it's not because things canceled. The reason why is that we had to multiply and divide by a 3 here, and we had to multiply and divide by a 4 here in order to get the sine of theta over theta form. So we had to multiply by a 3 in the numerator to get this 3 in the denominator, and we had to put this 4 in the denominator to get this 4 in the numerator. So that's why this 3 and this 4 showed up in the end result. Let's do one more example. Here we have the limit as x goes to 0 of 1 minus cosine of 4x divided by x squared. So this one, we're going to do a familiar trick now. We're going to multiply and divide by something that gives us a difference of squares. So we have 1 minus cosine of 4x over x squared, and we're going to multiply and divide by something that will give us the difference of squares. So it's going to be 1 plus cosine of 4x. But if you put it in the numerator, you have to put it in the denominator as well. So now we're going to have the limit as x goes to 0 of, and we just multiply a minus b times a plus b, and that's going to give us 1 squared minus cosine of 4x quantity squared, and all of this is divided by x squared times 1 plus cosine of 4x, like so. Okay, well, in the numerator, what do we have? We have the limit as x goes to 0 of 1 minus cosine of 4x quantity squared, divided by some stuff in the denominator. Well, what is 1 minus cosine of something squared? Well, by the Pythagorean identity, that's going to give us sine of something squared. So 1 minus cosine of something squared is sine of that thing, and then it's the quantity squared. And when I say quantity squared, I mean all of sine. And this one is divided by, and I haven't done anything to the denominator yet, x squared times 1 plus cosine of 4x. Okay, and the next step is to just group things together in the right way. So this is going to be the limit as x goes to 0 of sine of 4x over x times sine of 4x over x times 1 over 1 plus cosine of 4x. So how did we get all of this? Well, we have a sine of 4x times the sine of 4x is going to give us the sine of 4x quantity squared. We also have an x in the denominator and an x in the denominator, and that's the x squared. And here we have sine of 4x over x. Well, I want to turn this into sine of theta over theta, so I use what now is a familiar trick. And I just simply write a 4 in the denominator, like that. Well, if I put a 4 in the denominator, I have to put one in the numerator as well. Well, I do the same thing here, 4x and 4. So in this case, I'm going to use theta is equal to 4x. And what does that give me? Well, this limit, that's going to go to 4 times 1. 4 times 1. This one is going to go to 4 times 1, because here I have a sine of theta over theta. Here I have a sine of theta over theta, but of course we have a 4 here and a 4 here. And what about this term right here? Well, this is perfectly well behaved. It's 1 over 1 plus cosine of 0 is 1. So that's just going to go to a 1/2. So what do we end up with if we just go back up to here where we have an equal sign? This is going to be equal to 4 times 1 times 4 times 1 times 1/2, which is going to give us 16 over 2, which is 8. And that's our limit.